Hello, everyone, and welcome to another AP Chemistry virtual lesson. My name is Michael Faribaugh, and I teach AP Chemistry at Albemarle High School in Charlottesville, Virginia. Today, our lesson will start with Unit 6, Thermodynamics. Just want to remind you, as always, that you can go to apstudents.org/exams2020 to get more information about taking AP exams online this year. For AP Chemistry, your exam date is on May 14th. And as you can see here on the screen, it's going to be given at the same time. So depending on where you are in the world, you're going to be taking it at a particular time according to your time zone. There are two free response questions on the AP Chemistry exam. The first one will count for 60% of the exam weight and last 25 minutes. And the second question will count for 40% of the exam weight and will be 15 minutes. And you can see here on the screen, explain chemical phenomena using models, theories, representations at the particulate and macroscopic levels, draw conclusions from experimental results, identify and explain experimental procedures that are aligned to a question and analyze sources of error. So a lot of analysis. And so again, hopefully today's lesson will help you practice those skills. If you have a periodic table and something to write with and some scratch paper, let's go ahead and get started. So this is going to be an introduction to Unit 6, which is on thermodynamics. So the topics that I will cover today include endothermic and exothermic processes, energy diagrams, heat transfer and thermal equilibrium, heat capacity and calorimetry, and energy of phase changes. And you can see here on the screen the requisite science practices. Some of the things that I already talked about in terms of making observations and representing phenomena with graphing techniques, as well as talking about connections between the particulate and the macroscopic scales. So I will begin by talking about endothermic and exothermic processes. I'll talk about energy diagrams. We'll talk about the difference between energy, enthalpy, and heat transfer and thermal equilibrium, specific heat capacity and calorimetry, and the energy of phase changes. So typically before we dive into the content of our lesson, we start with a warm-up problem, and this would be the homework problem, the AP Chemistry problem that Mr. Byrne assigned in yesterday's lesson. So here we have number 1, it says in part A, chlorine gas is initially present in the container at a pressure of 0.40 atmospheres. And the first part of this question is to calculate how many moles of chlorine are in the container. So we have a pressure, we also have a volume, and we have a temperature. So hopefully you can think about the fact that we're going to be using the ideal gas law. We'll be solving for moles. So pressure is already in atmospheres, so we can use our ideal gas constant, 0.08206, and that does have units of liters, atmospheres, and then per mole per Kelvin. Now, the fact that it's Kelvin, be careful that you don't forget this important step, and that is you cannot plug in 120 into your calculator and get the right answer. So 120 plus 273 is going to equal 393 Kelvin. So it's the Kelvin temperature that you should be using to solve for moles. All right, well, if you did that particular setup using the ideal gas law, then the math you're doing on your calculator is 0.4 times 25 divided by 0.08206 divided by 393. And we're going to go ahead and round this off to 2 significant figures based on the least number of sig figs. So I got 0.31 moles of chlorine gas. So that takes care of the first part. Now the second part says how many grams of carbon disulfide are needed to react completely with the chlorine. So we're going to have to use our knowledge of stoichiometry and the fact that there is a 1:3 mole ratio between CS2, the carbon disulfide, and then the Cl2, the chlorine gas. Also remember to use your periodic table because we'll need to go to grams. So therefore you'll have to figure out what is the molar mass of CS2. All right, so I'll start with the answer from Roman numeral 1. That was the number of moles of chlorine that we got from the ideal gas law. Let's use the 1:3 ratio, which is given to us by the coefficients, to convert from moles of chlorine to moles of CS2. Then if we look on our periodic table, we see that carbon has an atomic mass of 12.01, sulfur has an atomic mass of 32.06, but there are 2 of them in the formula. That's 64.12. So for a grand total of 76.13 grams of CS2 per mole. So if we do this math, 0.31 divided by 3 times 76.13, we get our answer, which is 7.9 grams of CS2. And again, I'm just rounding off to 2 significant figures. All right, well, now on to a part of the problem that looks more relevant with respect to things like kinetics and reaction rates. So we are told that at 30 degrees Celsius, the reaction is favorable. In other words, it is supposed to occur. However, no reaction is observed. So it is favorable but not observed. And then at 120 degrees, the reaction occurs at an observable rate. It should not surprise you that when you raise the temperature of a reaction, you are going to increase the reaction rate, but you have to explain why. So explain how the higher temperature affects the collisions between the reactant molecules so that the reaction occurs at an observable rate at 120 degrees Celsius. It would not be acceptable to simply say higher temperature leads to a higher rate. You have to talk about the collisions. And I would probably at this point encourage you to mention activation energy. That is a key part of it. So the activation energy is going to be the energy required. And we can see that coming up on the graph that we're going to have to draw in part 2 of this question. So let me just remind you from something I talked about a while ago. This was back in Unit 3 on intermolecular forces. Here we see a liquid inside a flask, and the vapor pressure is going to be the pressure of the vapor above the surface of the liquid. And according to the graph, you can see that as vapor pressure increases, as temperature increases, there is a relationship there that higher temperature leads to a higher vapor pressure. So Mr. Byrne had talked about these Maxwell-Boltzmann curves. Here's an example of a Maxwell-Boltzmann curve for a colder temperature of the liquid. And here is the minimum kinetic energy required for molecules to escape. So you can see that only a small fraction of the molecules are going to have the ability to escape the liquid. And so what happens when we raise the temperature is we increase the average kinetic energy of the molecules. And so that curve shifts, and now a greater fraction of the molecules have the kinetic energy needed to escape. So instead of talking about kinetic energy needed to escape the liquid in a physical phase change, think of it as a chemical reaction. A greater fraction of the molecules will have the required activation energy when they collide. So at a higher temperature, the molecules have a greater average kinetic energy. Again, here's the part about the collisions, the fact that there's a greater number of molecules that have sufficient energy to overcome the activation energy. So they are not only colliding more often, but with more force. And again, that greater fraction of molecules that has enough energy to overcome the activation energy, that's a key part of this explanation. Now, they've already given you a graph for 120 degrees, and our job is to draw one at 30 degrees. Now, many students who got this question wrong on the AP chemistry exam did this. So they just assumed that it would be lower, completely just drawing a new curve that was underneath the first one. Hopefully you can see that that would not be correct, because we still have to have the same area under the curve. So we're going to be shifting this curve to the left because it's a colder temperature. Therefore, the peak of this curve, that is the average kinetic energy or the mean, has been shifted. But also this area under the curve is lower. Okay, so in terms of getting this particular question correct, this part of the question was worth 2 points on the scoring guidelines, 1 point for a student's drawing in which the curve has a peak that is above and to the left of the given curve. And then the second point is earned for a curve that is below the given curve in the region beyond the activation energy right there. All right, there was another homework problem that Mr. Byrne gave you, and that was, we have a reaction that's been broken up into two steps. We have a rate determining step, step 1, which is the slow step, and then we have step 2, which is a fast step. So our job is to write the rate law for the reaction that is consistent with the reaction mechanism. So focusing primarily on the slow rate determining step, we can see exactly one molecule of C2H4 and one molecule of HCl. So from that elementary step, we can say that it's first order with respect to C2H4 and first order with respect to HCl. So that gives us a rate law. Rate equals K times the concentration of C2H4 raised to the first power times the concentration of HCl raised to the first power. The next part of this question is identify an intermediate. So you could have picked either the C2H5 plus or the Cl minus. Either of them would have been correct because they are formed in step 1 and then consumed in step 2. So they are intermediates. Then we had to draw a curve. Considering that the reaction is going to have reactants and products, the reactants are C2H4 and HCl. Now, where should we draw the potential energy for the products? Should we draw it up here or should we draw it down here? It depends on whether the reaction is exothermic or endothermic. So we are given that there is a negative delta H. That means that it's an exothermic reaction. So we should focus on the products being at a lower energy level than where we started. So the correct curve should look something like this, but I made a mistake in that this curve that I've just drawn indicates, although it's exothermic, that the reaction occurs in a single step. Notice that we have just one activation energy, one little hill to climb over. We know this is a two-step reaction, so we have to show that with our curve. We have to show the first step, which is going to have a higher activation energy, and then the second step, which is going to have a smaller activation energy. So in sort of colloquial terms, it's a big hill and a small hill. So this would be the activation energy for the reaction. So we're showing the activation energy for the rate determining step, and that would be that first step. The higher the activation energy, the slower that particular step is. All right, so now moving on to our information about thermodynamics today. I'd like to start with endothermic and exothermic processes. And here I have two little examples of this might occur. You've got a instant cold pack, and it's the kind of thing you can sort of squeeze this bag, and there's a pouch of water inside, and you squeeze the bag until the pouch of water breaks, and it dissolves a particular solid. It's an endothermic process for an instant cold pack, and it's an exothermic process for an instant hot pack. So instant cold packs are doing something with respect to energy that's the opposite of what an instant hot pack is doing. Let me just help you identify exactly what's going on in terms of energy. So for an endothermic process, energy is transferred from the surroundings to the system. So the system is the dissolving of that solid that's inside the instant cold pack into water. Now, when we feel the cold pack, it feels cold because our hand is part of the surroundings. The system is going to be the water and the dissolving solid. The surroundings are everything else, the container and everything outside it. So for an instant hot pack, it's an exothermic process. Now energy is transferred from the system to the surroundings. And again, since our hand is part of the surroundings, we touch the hot pack and it feels warm. So let's be clear on the direction of energy flow. For endothermic and exothermic processes, let's also define the system and the surroundings. So we define the system as the portion of the experiment on which we choose to focus our attention, which is normally the reactants and the products. For a chemical change, or even for a physical change, it would be the chemicals that are changing, combining, dissolving, melting, things like that. And the surroundings are everything else, the container and everything outside. Now, there's an important note which will come up later in this lesson. If you are dissolving a solid in water, The thermometer, which is used to record the temperature, is considered to be part of the surroundings. My students really struggle with this in my class when I say that something gets colder and it's endothermic, because in their mind, they're thinking, well, if it's absorbing heat, why isn't it getting warmer? It is absorbing heat, but typically from the surroundings, and therefore the surroundings are getting colder. The thermometer is part of the surroundings. So when you release energy to the surroundings, the thermometer goes up, the temperature goes up. And when you absorb energy from the surroundings, the temperature goes down. All right, so we have something known as the first law of thermodynamics, also known as the law of conservation of energy. Energy cannot be created or destroyed. It can change from one form to another. And again, for an endothermic process, heat is absorbed by the system. And for an exothermic process, heat is released to the surroundings. Now, since even though this is a chemistry lesson and not a physics lesson, you all that are in physics classes or have taken physics might know that there is more than just heat. Another common form of energy, which is used in various calculations in physical science, is work. So work done on the system, again, energy is still going into the system, is endothermic. Work done on the surroundings, so energy is leaving the system, it's exothermic. We spend the majority of our time in chemistry focusing on heat and not on work, and I'll talk about that a little more later. So this person is exercising and they are perspiring. So how exactly does perspiration cool the body off? Well, here's a close-up view of what's happening. There's a little drop of sweat that contains water molecules, and the water molecules evaporate. That means that the water molecules are changing from a liquid to a gas. So do you think that evaporation is an endothermic or an exothermic process? Remember that perspiration or the evaporation of that perspiration is going to cool the body. So is the process of changing water from a liquid to a gas endothermic or exothermic? Well, it is endothermic because you have to absorb energy to change the molecules of liquid to a gas by separating the intermolecular forces between the liquid. So if it's taking in energy, where is the energy coming from? Well, it's coming from the body. So heat is removed from the body as perspiration evaporates. The water is part of the system. In this case, the evaporation of water involves the water molecules, and the body is part of the surroundings. So heat is flowing from the surroundings to the system. The body is losing heat and the water is gaining heat. Now let's talk about energy diagrams. We can represent energy along the y-axis. And if you see a diagram like this or like this, you can see that the products are at a higher energy level than the reactants. Earlier in one of the practice problems that I showed you in our warm-up, it was an exothermic process, so it was actually the opposite. It was downhill, where the products were at a lower energy level than the reactants. So if you see an energy diagram, you can tell that the energy diagram is either endothermic or exothermic by comparing the reactants and the products. So endothermic looks like this, and exothermic looks like that. All right, now the words energy and enthalpy and heat are often used in chemistry interchangeably. So let's pay close attention to these words for a moment. Energy in general is the capacity to do work or transfer heat. So some textbooks define the change in internal energy as delta E, and they refer to the delta E as the sum of the heat, which we're going to call Q as a symbol, and work, W. If the change in energy is the sum of the heat and the work, what exactly are heat and work? Well, heat is the transfer of energy that takes place because of a difference in temperature. Heat spontaneously transfers from the warmer object to the colder object. So if you touch, let's say, something hot on the stove, then the energy is transferred from the stove to your hand. But if you're holding an ice cube, and the ice cube starts to melt, now the heat is being transferred from your hand to the colder ice cube. Work is the exertion of a force through a distance, and sometimes represented in physics as force times distance, or it can also be represented as pressure times the change in volume. And there's a negative sign there because if work is being done on the system, while that's a positive value, the delta V would be negative. Effectively, what I'm saying when I say the delta V is negative is if you're doing work, so for example, let's say I have a piston and I'm compressing a gas inside a piston, so I have to change the volume. By decreasing the volume, delta V would be negative, but therefore, since I have a negative times a negative, it would be positive, as in work being done on the system. Again, we're going to spend the majority of our time focusing on heat and not work. And that's because in chemistry, many phase changes and chemical reactions occur at constant pressure. That brings up the concept of enthalpy. So enthalpy is used to measure changes in energy for a constant pressure system. And because enthalpy is defined in this way, which is the sum of the delta E and then this pressure volume work, it turns out that when we talk about enthalpy, we effectively are referring to the heat. So while they are not exactly the same thing, for all intents and purposes, when you hear a chemistry problem refer to the change in enthalpy, it is essentially the change in heat energy that we're focusing on. So typically we're not talking about pressure volume work for most processes in chemical reactions and phase changes. Now, in terms of that change, if delta H is positive, that means that the difference between products and reactants is a positive value. That's endothermic. But if the difference between products and reactants is negative, that's an exothermic process. An important point to clarify here is Q versus delta H. If an AP question asks you to calculate the value of Q, they typically are referring to the magnitude of heat that is either absorbed or released. And so for problems like that, they don't normally ask for the sign of Q. So the magnitude of Q, or the absolute value, is how much energy was absorbed or how much energy was released. And the units of Q are typically joules or kilojoules. Now, if instead the question says, calculate the value of delta H, pay close attention to whether it's an endothermic or an exothermic process, because you might miss a point on the AP exam if you forget to include the proper sign, especially if it's negative and you don't include that negative sign for an exothermic reaction. That's important. Now, the units of delta H are typically kilojoules per mole or kilojoules per mole of reaction. So stoichiometry and potentially a balanced chemical equation may come into play. So be careful that you know the difference between Q, which is heat, and delta H, the change in enthalpy. All right, just a brief comment about heat transfer and thermal equilibrium. Suppose we have a sample of copper metal and we place it in a bath of boiling water at 100 degrees Celsius. So now we have this hot piece of copper metal. We take it out of the boiling water bath and we quickly transfer it to a styrofoam cup that contains a sample of cool water at 20 degrees Celsius. Now, heat transfer and thermal equilibrium, at some point, the temperature of the copper will become the same as the temperature of the surrounding water. So heat is transferred from the hotter object, in this case the metal, to the cooler object, in this case the water. The atoms of metal are slowing down, the molecules of water are speeding up, and eventually thermal equilibrium is reached, in which the substance has each substance has the same average kinetic energy, which means they have the same temperature. So when heat is transferred from a warmer object to a cooler object, eventually that transfer will continue until thermal equilibrium is reached. So that experiment of transferring a hot piece of metal to a cooler cup of water is a rather classic thermochemistry experiment. So you might have actually done this in your chemistry class, or you might have seen a demonstration about this. Here I have a data table with information about how much the copper weighs, 50 grams. The initial temperature of the copper was 100 degrees Celsius because it was sitting in a boiling water bath, and that is the boiling point of water. The mass of the water in the styrofoam cup, 100 grams. Initial temperature of the water, 20 degrees Celsius. So when thermal equilibrium was reached, the final temperature of both the copper and the water was 23.6 degrees Celsius. Okay, this is a rather easy set of questions to ask you. Then I'm going to ask you to agree with a particular claim that is made by a student. So here are two easy questions. First, what's the delta T? What's the change in temperature for the copper? And notice I'm talking about the absolute value of this. Don't worry about the sign being positive or negative. So I'm not worried about T final minus T initial, just the magnitude. So the delta T for the copper. Well, if you're looking at the data table, the math you're doing is 100 minus 23.6. So our delta T for the copper is 76.4 degrees Celsius. All right, what's the delta T for the water? The change in temperature, just the absolute value, the magnitude. Well, that's going to work out to be 23.6 minus 20, 3.6 degrees Celsius. Okay, here comes the student claim. Decide if you agree with this claim. A student claims that since the magnitude of delta T for the copper is greater than that of the water, it means that the magnitude of heat, Q, lost by the copper is greater than the magnitude of heat gained by the water. Do you agree with this claim? And again, feel free to pause the video if you want to think about this before checking the answer. You have to make a decision. Is the magnitude of heat lost by the copper less than, more than, or equal to the magnitude of heat gained by the water? Well, earlier I talked about something called the first law of thermodynamics, also known as the law of conservation of energy. It states that energy cannot be created nor destroyed. It can change from one form to another. If we make the assumption that this styrofoam cup is perfectly insulated and that no heat is lost to the surroundings, according to the first law of thermodynamics, the magnitude of heat lost by the copper must be equal to the magnitude of heat gained by the water. Now, how do we calculate this in terms of calorimetry? So on your equation sheet on the AP Chemistry exam, there's lots of equations in this section under thermodynamics, but I'm focusing on this one, which involves heat, M for mass, C for something called the specific heat capacity, and then T for temperature. Let's think about what exactly is the specific heat capacity, and let's talk about units. So for water, it turns out that the specific heat capacity is 4.18 joules per gram degree Celsius. Sometimes you will see this listed as joules per gram Kelvin. Either one of those is actually fine, Celsius or Kelvin, because the change in temperature either way is the same magnitude. If a thermometer goes up by 10 degrees, it will also go up by 10 kelvins. So what this means is that it requires 4.18 joules of energy, of heat energy, in order to raise the temperature of 1 gram of water by 1 degree. Now, copper, aluminum, glass, sand, iron, all kinds of substances have their own values for the specific heat capacity. And the units are going to be joules per gram degree Celsius. I just gave you the value for water, but the specific heat capacity for copper is unknown to us. We can use the equation Q equals mc delta T to help us determine the specific heat capacity of copper. Again, a common experiment in chemistry class under the category of thermochemistry or thermodynamics. So how we're going to do this is based on the fact that the heat that was lost by the copper is equal to the heat gained by the water. So mc delta T for the copper is equal to mc delta T for the water. And we know everything except for the specific heat capacity of the copper. We know the mass of the copper is 50 grams. We know that the change in temperature of the copper was 76.4 degrees. We know that the mass of the water is 100 grams. And we know the specific heat capacity of the water that was given to us. And the change in temperature for the water is 3.6 degrees Celsius. So all I have to do is just get C, the specific heat capacity for the copper, on a side by itself. I'll just divide both sides by 50, and 76.4. My units of grams will cancel out. My units of degrees Celsius on the right will cancel out, but I will still have my final answer in units of joules per gram degrees Celsius. So if you do on your calculator 100 times 4.18 times 3.6 divided by 50 divided by 76.4, you get 0.39 joules per gram degrees Celsius. So that is our experimental value, and it's very much the correct value. I did this by checking the official value, and that is the accepted value for copper. So 0.39 joules per gram degrees Celsius. Now, I want to ask you a conceptual question. It does not require calculation, but I will still do some math to kind of verify our prediction here. Suppose you have each of these samples, same mass, different specific heat capacity, same initial temperature. And each of these samples absorbs 500 joules of heat. So the conceptual question is, which sample, the water or the copper, will reach a higher final temperature? Justify your answer. Again, feel free to pause the video, think about this before the answer is revealed. Okay, well, before I tell you the official answer and do some math, remember that there is this is your focus. It's the same heat, it's 500 joules. It's the same mass, it's 100 grams. So look at this relationship between these two variables. If that is a direct relationship, that means that as one value goes up, the other value also goes up. If it is an inverse relationship, that means that as one value goes up, the other value goes down. When you multiply two variables together to equal a constant, that represents an inverse relationship. So therefore, the higher the specific heat capacity, the smaller the delta T. So if the question was asking which of these two substances is going to reach a higher final temperature, the correct answer is going to be the copper, because it has a smaller specific heat capacity, then its delta T will be larger. Now, we didn't have to do any math to answer that question, but let's go ahead and do it. So we have Q equals MC delta T for the water. That's 500 joules, 100 grams, 4.18, and we don't know the delta T. So we'll go ahead and solve for delta T, and we get 1.2 degrees Celsius. So the final temperature of the water is 25 plus 1.2, 26.2. For the copper, we have Q equals MC delta T. Now we have plugged in our information. Again, a smaller magnitude of the specific heat capacity leads to a larger delta T. So the copper has gone up by 12.8 degrees Celsius for a final temperature of 37.8 degrees Celsius. Now, I probably should have said 25.0 degrees Celsius, so I would have the proper sig figs, but I'm just focusing on the magnitude here. So again, inverse relationship between the value of C and the value of delta T. Sometimes you will see molar heat capacity, and the units are not joules per gram degrees Celsius, but rather joules per mole degrees Celsius. So can we take 0.39 joules per gram degrees Celsius and multiply by some conversion factor that will give us joules per mole degrees Celsius? So what's missing here in this conversion factor would be something that will put grams on the top and moles on the bottom. So all we really have to do is consult our periodic table to do this conversion. So the periodic table tells us that copper has a molar mass of 63.55 grams per mole. If we do this math and the units of grams cancel out, the molar heat capacity of copper is about 25 joules per mole degrees Celsius. Okay, next thing I'd like to talk to you about is the energy of phase changes. What I have here is a diagram involving heat on the x-axis and temperature on the y-axis. I want to focus on the phase change of water. I'm going to look at the melting point of water, which is at 0 degrees Celsius, and the boiling point of water, which is at 100 degrees Celsius. So I have drawn horizontal lines on the diagram indicating the melting and the boiling point of water. Now, suppose I start off with some solid H2O, some ice, at around negative 40 degrees. As heat is added, the temperature rises. The reason why the temperature rises is because I am warming a substance, in this case, solid water, and I would calculate the amount of heat required to raise the mass of water by a particular value of degrees Celsius using Q equals mc delta T. So now I am at the melting point of water. What happens when more heat is added? Will the temperature continue to rise steadily up to 100 degrees Celsius as the ice melts? No, in fact, we reach a plateau. And this particular plateau means that we are not talking about mc delta T because our delta T is actually 0. And yet heat is being added. So this is what's known as the enthalpy of fusion. And fusion is essentially a fancy word for melting. So the enthalpy of fusion involves the transfer of energy from a solid as it's converted into a liquid. Some of the intermolecular attractive forces between the solid crystal particles are broken, and now we have water in the liquid state, but we are still at 0 degrees Celsius. If we add more heat, now that we have converted the solid completely into a liquid, the temperature starts to rise again. So we're back to mc delta T, the change in temperature for a liquid. So we are warming a liquid. Incidentally, there is a different specific heat capacity for water, whether it is a solid or a liquid or a gas. Okay, well, now we're at the boiling point of water and we have to add more heat. We reach another plateau. At this point, we are breaking not just some, but all of the intermolecular forces. So if we're breaking all the intermolecular forces as we go from a liquid to a gas, hopefully you can see it's going to take more heat to change a substance from a liquid to a gas than it does to change a substance from a solid to a liquid. So this is not the enthalpy of fusion. This is the enthalpy of vaporization from a liquid to a gas. Now we're at the state where all of the liquid has been converted to a gas, and we can continue to heat this gas to temperatures above the boiling point, and we're back to mc delta T again. So what I'm showing you is a phase diagram or a heating curve. And this particular heating curve has slanted lines as well as flat lines. The flat lines are when phase changes occur, and the slanted lines are when you're just warming one of the phases. So either warming a solid or the solid melts, you're warming the liquid evaporates or boils, and then you're warming the gas. You can see on this slide that we have different values for the specific heat capacity of water, whether it is a solid or a liquid or a gas. You'll also notice that when we do the enthalpy of fusion, that line segment is smaller than when we do the enthalpy of vaporization. So 40.7 is a larger number than 6.01. It takes more energy to evaporate the liquid than to melt it. So what I'm showing you for calculations along the flat regions is not mc delta T, but rather number of moles. So N is number of moles multiplied by the delta H for that phase change. So the units are typically kilojoules per mole for the enthalpy of a phase change. Multiplying by the moles will give you kilojoules. Okay, we've talked about water. Here is the phase, I'll call it a heating curve, not a phase diagram, but heating curve for methane. Same kind of process. You have a slanted line, a flat line, and so forth. And so we have the enthalpy of fusion for methane is 0.94 kilojoules per mole, and the enthalpy of vaporization for methane is 8.2 kilojoules per mole. In terms of intermolecular attractive forces, and again, this was methane. I said it, didn't actually write it, sorry. Methane is CH4. In terms of intermolecular attractive forces, explain why line segment S is much longer than line segment Q. Well, I've already talked about this, so I'll kind of go quickly to the answer. During line segment Q, the substance is changing from a solid to a liquid. Only some, but not all, of the intermolecular forces are broken. During line segment S, the substance is changing from a liquid to a gas. Essentially, all of the intermolecular forces are broken, so it takes more energy to completely separate the molecules from each other in the transition from liquid to gas than it does to separate the crystal into the liquid phase. Another question I can ask you that relates to water and methane is the following. We have the delta H of vaporization, the enthalpy change for the vaporization, that's liquid to gas. For methane, it's 8.2, and for water, it's 40.7. In terms of intermolecular attractive forces, explain why the value of the enthalpy of vaporization for water is much greater than the value of the enthalpy of vaporization for methane. You should talk about the specific intermolecular forces in your answer and compare the relative strengths. So from an earlier lesson back in Unit 3, talking about intermolecular forces, you might recall that a molecule like CH4, which is tetrahedral, and all the dipoles cancel out, is nonpolar. It only experiences weak London dispersion forces, whereas water is polar and experiences both London dispersion forces and hydrogen bonding attractions. And so the intermolecular forces in water are stronger than those in methane. So more energy is required to convert water from a liquid to a gas, and that's why 40.7 is higher than 8.2. All right, a few more AP practice problems, and then I'll get to your homework. Here is an AP practice problem that is relevant to today's lesson. Some building materials contain small capsules filled with paraffin wax to improve the insulating properties of the materials. The melting and freezing of paraffin inside the capsules in the material helps to regulate temperature. Paraffin wax begins to melt at 37 degrees Celsius. Part A of this question says, while the wax is melting, is the net flow of heat or thermal energy from the wax to the surroundings or from the surroundings to the wax? Justify your answer. Again, feel free to pause the video because I'm going to go relatively fast from the question to the answer. So if you don't have enough time to think, then feel free to pause the video before I reveal the answer. Okay, so the answer here is that melting is an endothermic process. So therefore, thermal energy flows from the surroundings to the wax. Again, the wax is absorbing heat from the surroundings as melting occurs. Part B of this question says, calculate the amount of thermal energy that is required to melt 15.2 grams of solid paraffin wax. So again, that's at the melting point. We have the molar mass of paraffin is given to us, as well as the molar heat of fusion. All you really have to do is 2 conversion factors to get from grams of wax to kilojoules. So you're going to have to first go from grams to moles, and then you're going to have to go from moles to kilojoules. You're already given the molar heat of fusion, that's going to go right here, and you're also given the molar mass, and that's going to go right there. So we're going to go from grams to moles, and then moles to kilojoules. So here's my first step, and there's my second step. And if you do this math, 15.2 divided by 282.62 times 48.78, your final answer in kilojoules, 2.62. All right, the next part of this question, when paraffin wax melts, its density increases. Provide a particle level explanation of this observation. So density is mass over volume. So why is the density going down? Hopefully you can realize that when you melt something, you are not changing the mass, but we are changing the volume. So think about in what way would the volume be changing as we go from a solid to a liquid if they're telling us that the density decreases. And the correct answer is the following. In liquid paraffin wax, the average distance between the molecules is greater than in the solid state. So they're taking up more space as a liquid than as a solid. So the same number of molecules now occupies a larger volume in the liquid state. So the density of the liquid would be less than the density of the solid. All right, moving on to our next AP practice problem. Again, relevant to this lesson. A student investigates the enthalpy of solution, so there's delta H of solution for two alkali metal halides, lithium chloride and sodium chloride. In addition to the salts, the student has access to a calorimeter, which for most laboratories, that would be a set of styrofoam coffee cups for insulation, a balance with a precision of 0.1 gram plus or minus, and a thermometer with a precision of plus or minus 0.1 degrees Celsius. We're going to focus on the lithium chloride. It says in part A, to measure the delta H of solution for lithium chloride, the student adds 100.0 grams of water. And there's the initial temperature of 15.0 degrees Celsius. Then they add 10.0 grams of solid lithium chloride and they stir to dissolve. Now, did the dissolving process represent an endothermic process, in your opinion, or an exothermic process? In other words, was heat released to the surroundings, as in exothermic, or was heat absorbed from the surroundings, endothermic? Remember that the thermometer is typically considered to be part of the surroundings. That's important that you understand that, because they're going to ask you for the delta H in Roman numeral 2, and if you get the wrong sign, you might not get credit for this. Okay, so consider what we have. Calculate the magnitude of heat absorbed. Let's use MC delta T. Now it does say by the solution, and they say the specific heat capacity is of the solution. So the most common mistake that students make is this. They put M as in mass of water. Well, that's not the solution, that's just the water. We still have a solution that contains both solute and solvent. So you have to consider the mass of the solution, not just the water. So the correct answer is going to have 110 grams. That's the mass of the solution, the specific heat capacity, which they gave us, and then the delta T, 35.6 minus 15.0. That's a difference of 20.6. Our answer will come out in joules. So 110 times 4.18 times 20.6 is 9,470 joules when I rounded this off to 3 sig figs based on the least number of sig figs in my measurement. And you could write that as either 9,470 joules or 9.47 kilojoules, because they didn't give you a specific unit. They just said calculate the magnitude of heat. No sign is important right now, but now the sign is important. So we're going to have to figure out the number of moles because it's kilojoules per mole. And since 10 grams of lithium chloride, let's go ahead and add up. Lithium chloride would be 6.94 plus 35.45. 42.39 is the molar mass of lithium chloride. This gets us part of our answer. So 9.47 kilojoules. 9.47 kilojoules divided by 0.236 moles. Okay, if I do this math, I'm going to get an answer. Is it going to be the correct answer? Well, that depends. Is it a positive or a negative? Is it an endothermic process or an exothermic process? Remember, when a solid is dissolved in water to form a solution, the thermometer is considered to be part of the surroundings. And the surroundings got warmer. It's an exothermic process, so delta H should be negative. The correct answer is not 40.1, but rather negative 40.1. And you could say kilojoules per mole or kilojoules per mole of reaction. All right, next part of this question that I want to talk about is actually part F. I'm skipping B, C, D, and E. So in part F of this question, they had asked the lattice energy the lattice enthalpy of lithium chloride is positive, indicating that it takes energy to break the ions apart in lithium chloride. However, the dissolution of lithium chloride in water is an exothermic process. Identify all particle-particle interactions that contribute significantly to the dissolution process being exothermic. So remember that forming a bond is an exothermic process. Breaking bonds is endothermic. We're focusing on the exothermic process. So therefore, it's going to be the bonds that are formed, the attractions that are formed between the solute and the solvent, and those are known as ion-dipole interactions. You cannot talk about the strength of the ionic bonds or the hydrogen bonds between the water molecules because those are being broken, some of them, in the formation of the solution. So it's got to be the formation of the attractive forces in this case that would release energy, and those are ion-dipole forces. All right, another quick AP practice, then we'll get to our homework. Aluminum metal can be recycled from scrap metal by melting the metal to evaporate impurities. Calculate the amount of heat needed to purify 1 mole of aluminum at 298 Kelvin by melting it. The melting point of aluminum is 933 Kelvin. So first we have to actually warm up the aluminum from 298 to 933. That would normally be MC delta T, but they've given us a molar heat capacity. So it's not joules per gram Kelvin, it's joules per mole Kelvin. The change in temperature is going from 298 to 933. That's a difference of 635 Kelvin. So it takes about 15,240 joules to warm 1 mole of aluminum from 298 to 933. It's about 15 kilojoules. And then it takes an additional 10.7 kilojoules of heat to melt it. So a total of 15 plus 10.7, and rounding off to no decimal places when you add two numbers, that would be 26 kilojoules to essentially purify and recycle this aluminum. Here they give us a chemical equation for extracting it from aluminum oxide, the ore. Now, it requires 1,675 kilojoules for every 2 moles of aluminum. So 1,675 kilojoules for every 1 mole of reaction, which is for every 2 moles of aluminum. That's 837.5 kilojoules. Since 26 kilojoules, which is the recycling, is much less than 837.5, recycling requires less energy than extracting. All right, well, thank you for hanging in there with me. We talked about endothermic and exothermic processes today, energy diagrams, heat transfer, enthalpy, specific heat capacity, and calorimetry, energy of phase changes. So these 3 slides will be your homework. This is slide number 1. This is slide number 2. And this is slide number 3. I will be going over the answers to this question in my next lesson, which will be on Monday. Don't forget to check out the helpful chemistry resources in the link in the video description. Thanks for watching. This has been Michael Faribaugh from Albemarle High School in Charlottesville, Virginia. And I want to remind you that if you haven't already contacted the College Board, if you need mobile tools or connectivity, please let them know by Friday, April 24th. That's 1 week from today. That is the deadline. All right. Have a good rest of the day and a good weekend. I'll see you back here on Monday. Thanks for watching.